Good morning, friends. Today we'll start the third chapter, primes and theory of congruences. So, in divisibility of integer chapter, I have defined the concept of prime number and composite integer. Here also, again I am revising definition of prime, then composite integers. Okay. So, what is a prime integer? An integer except plus minus 1 is said to be prime integer if it has no proper factor. So, if it is only divisible by plus 1, minus 1 plus p minus p, then it is called as prime integer. Okay. So, an non-zero integer p not equal to plus minus 1 is said to be prime integer if it is only divisible by plus 1 minus 1 and plus 1 minus p only. Okay. That is, if it has no proper factor, proper divisor or factor, right, then it is called as prime integer. Okay. Then composite integer, so here example plus minus 2, plus minus 3, plus minus 5, plus minus 7 and so on. Then composite integer and non-zero integer and a non-zero integer n not equal to plus minus 1 is composite integer if it has proper factor. If it is not prime, that is, if it has proper factor or divisor. If I take example plus minus 4, plus minus 6, plus minus 8, plus minus 10, plus minus 12 and so on. Here I forget to write plus minus 8, plus minus 9, plus minus 14, plus minus 15 and so on are composite integers. Okay, are composite integers. Now we'll take Euclid's lemma. If p is prime integer, and AB belongs to Z are such that P divides AB, then P divides A or P divides B. If P divides product of prime integer divides product of two integers, then it must divide one among them. Okay. So proof. So here p is a prime integer. Such that p divides ab for ab belongs to Z. If p divides a, then the result hold. If p doesn't divide a, p doesn't divide a, then p and a has no common factor, right? Because p is only divided by plus 1 and minus 1, plus p and minus p, and p is not dividing a. Then common factors for a and p is just plus minus 1. Okay. Then GCD of AP is 1. GCD of AP is 1. Therefore, since p is prime, and therefore any prime integer is always relatively prime to non-zero integer a, or its GCD with p is always p. Is always p, but p doesn't divide a. Okay. Therefore, x plus py is 1 for some xy belongs to Z. Xy belongs to Z. Now multiplying by b. Multiplying by b, we get abx plus pby is equal to b. This is 1. Okay. Now since p divides ab, implies ab is equal to pk for some k belongs to Z. Using 2 in 1, I will put value of ab. Okay. Using 2 in 1, we get pkx plus pby is equal to b, and therefore p in bracket or p into k dash is equal to b, where k dash is equal to kx plus by. This belongs to Z. So b is multiple of p, implies p must divide b. Okay. Thus p divides ab implies p divides a or p divides b. P divides b. Hence the proof. So this result is proved. Now we will take the corollary. If p is prime and p divides product of n integers. Okay. So corollary by using this. Let p be prime integer such that p divides a1, a2 dot dot up to an, then for a1, a2 dot dot up to an belongs to Z, then p must divides ai for at least one I. Sorry. For n equal to 1, P divides A1 implies P divides A1. For n equal to 1, n equal to 2, if P divides A1 A2, then P divides A1 or P divides A2 by Euclid's lemma. Euclid's lemma. Assume result hold for K. Assume result hold for K. That is, if P divides A1 A2 dot dot up to AK, then P must divide AI for at least one I. For at least one I belongs to 1 to up to K. Now if P divides A1 A2 dot dot up to AK plus 1, then P divides A1 A2 dot dot up to AK or P divides AK plus 1 by Euclid's lemma. If P divides A1 A2 AK, then P divides AI for some I belongs to 1 to up to K. So this is say 1 by 1. Thus, P divides A1 A2 AK plus 1 implies P divides AI for at least one I belongs to 1 to up to K plus 1. And therefore, by principle of mathematical induction, result must hold for any n belongs to n. Therefore, by principle of mathematical induction, result hold for any n belongs to n. That is, if P divides product of n integers and P is prime, then P must divide one of them, at least one of them. So, with help of this, now I will take one example. Let P be prime integer, let P be prime integer such that P divides A and P divides A square plus B square for AB belongs to Z. Then P divides B. In fact, here if I take A raised to n plus B raised to n also, result is also true. Okay. So, since P divides A and P divides A square plus B square implies P must divides A square plus B square minus A into a square. Since if p divides a, okay, or p divides x, p divides y implies p divides mx plus ny, or any mn belongs to Z. Okay. So this gives us this result. I am taking one here and here, a into a. Then this a square get cancelled. This implies p divides b square. Implies p must divides b square, b, since p is prime. So this is b into b. So if prime is divided product of n integer, it must divide one among them. So we will get this by corollary. In general, if prime p divides a and p divides a raised to n plus b raised to n, then p divides b, n belongs to n. This must hold. This must hold. Okay. Next example. Show that square root p is irrational number for any positive prime p, for any positive prime p. Solution. On contrary, suppose root p is rational number for some positive prime integer p. Then rational number is expressed as quotient of two integers where their GCD is 1. Then I can write p is equal to a upon b for some ab belongs to z such that GCD of ab must be 1. This implies root p is equal to a upon b for ab belongs to z where GCD of, for some ab belongs to z where GCD of ab is 1. This is 1. Okay. And therefore p is equal to a square upon b square. Therefore a square is equal to pb square. This implies p divides a square. This implies p must divides a since p is prime. And by Euclid's lemma. So this is 3 now. And therefore a equal to pk for some k belongs to z. This is 4. Using 4 into we get, what will get? P square k square is equal to pb square. So 1 p will get cancelled, and therefore p times k square is equal to b square implies this implies is b square is multiple of p, therefore p must divides b square. Implies is p divides b. Since p is prime and Euclid's lemma. Euclid's lemma. So this is my 4. So from 3 and 4, 3 and 5. 3 and 5, GCD of AB is greater or equal to P greater than 1, since P is positive prime. So GCD of AB is greater than 1. This is contradiction to GCD of AB is 1. And therefore our assumption is wrong. Implies square root p is irrational number for any positive prime integer p. Square root of negative prime integers are complex numbers. So it is not irrational number then. So with this discussion, today we will stop our lecture here. Thanks for listening lecture carefully. If you like lecture, give some comment and subscribe the channel. Bye bye. Okay. So I am keeping this for you for writing the notes.